Here we are again. This time we're going to take another look at the motor principle, something again that you learned about in grade 11, the motor principle. And you understand hopefully that it's basically a clever way of causing two different magnetic fields to interact with each other to actually produce a force, a magnetic force. And of course we've used this magnetic force. It's called the motor principle, you might think, because we use this to make motors. But the word motor actually just means to move. Maybe you've heard of fine motor skills, which are the movements of your fingers, tiny movements of your fingers. So a motor as a device is named after the idea of motion, and of course the motor principle is named after the motion that's caused by this magnetic force, or this overlap of two different magnetic fields. So let's just draw a couple of simple pictures. I say simple, but not so simple, because the motor principle is a little bit hard to get your head around. So what I'm going to do is I'm going to imagine a magnet here, the tip of a magnet. Let's call this the south pole of a magnet. And then down below here, I'm going to draw a picture that represents another magnet nearby, and this is the north pole of that magnet. And we know that between the two magnets, there would be magnetic field lines that run north to south. So I'm going to draw these magnetic field lines in. And as long as we stay in between the two magnets, this field will be very constant and unchanging. Of course, if we go too far off to the sides, if I get too far, out here, well, the field will start to do some wacky things. It'll start to bend and it'll start to lose its consistency. But in between there, it's a pretty constant magnetic field. Now, here's how I'm going to refer to this as the permanent magnetic field. And the reason I'm going to call it permanent is because it doesn't really change much. It's not caused by a current of electricity, so it doesn't actually depend on anything. I suppose if you move the magnets further apart, you could change it. But as long as the magnets stay put, this magnetic field is permanent and it will stay there. Permanent magnetic field. And we'll give it a little B, right? We'll call it B, the permanent magnetic field. Okay. Now I want you to imagine the second picture, totally separate from that. I want you to imagine a wire, and I want you to look at the wire in a cross section. So here's the wire, and you're looking at it cut and cross, and we're going to say that the current in the wire, the positive conventional current, so we're going to use a right-hand rule, is going to go away from us. Remember how we use the X to show that this is a wire running into the board or into the computer screen, and it's the current is going away from you into the computer screen. If we use a right-hand rule, we can see that it will produce a magnetic field also. And that magnetic field will be around the conductor. This is Oersted's principle. And we can draw it as concentric circles, something like this. And we can see from our right-hand rule, our thumb points in, our fingers would wrap this way, and this field would have a direction like this. Okay, so picture number one is two magnets doing their thing. Picture number two is a wire with electricity in it doing its thing, both of which have created magnetic fields. Well, somebody somewhere got the bright idea to put them together. Somebody said, why don't we just put them together and see what happens? So let's draw a composite picture of both. Let's draw our magnets again, right? And we'll put the other magnet way down here. And we said this was a south pole and this was a north pole. And let's put our little wire inside here. I'll draw them a little bit smaller. And our X to show the current going away from him. Well, now that they're together, the two fields are going to overlap. I didn't call this one anything, but if you wanted to do, I guess it would make sense to call it the induced magnetic field, because it's induced by the current in the wire. It's actually caused by that current flow. All right? Well, when you have two magnetic fields overlapping, guess what? They add together. They are vectors, they have direction, and they add as vectors. So technically you'd have to look at all the different components and add them all together. That's a complicated task, but we can get a good picture of what would happen just by looking at these two pictures, right? And by envisioning what would happen. So what I'm going to do is I'm going to show the old field from the other picture over here on this side. It's not part of the picture, but I want you to be able to see it. Okay, so let's put that over here. And over here, I want you to just remember that the other magnetic field looked like this, right? Circular, sort of. And of course, remember the direction. It was sort of to the right at the top and sort of to the left on the bottom, okay? Around the wire. So our wire's in there, right there. What we're going to try and do is we're going to try to draw in nice purple color here what the magnetic field might look like if we put the two together. Now remember something very important. This green magnetic field is not constant. Unlike the red one, which is pretty much the same strength all throughout this space, this green one, better use a different color, this green one actually gets weaker as you go out. So it's strong here, but it's weak out here, right? And so we have to remember that when we're doing our picture. So let's imagine if you were sort of following these magnetic field lines in your little magnetic boat. Well, down here, you'd feel a strong push upwards as you were riding up the red arrow. But as you got closer, you'd start to feel a little bit of a pull, sort of, see down here, you'd start to feel a little bit of a whoop as you encountered these green spinning magnetic fields. But you're far away from the wire, so you're pretty weak. So you might feel a little weak sort of tendency to slide around and then back. When you get around this side, you'd sort of slide back again, and then you'd be so far away that you'd just go right up like that. But now if you moved in a little closer, you'd feel that green little pull a little stronger, and it would pull you over this way a little stronger this time, and then pull you back, and then you'd go back up, something like that. And then, if you were here, you'd feel, now you're even closer. So now you're going to really feel that green swinging pull there when you're going to come back like this. So you see what's happening to the field lines. They're getting twisted by the green field, which is sort of spinning clockwise nearer the wire you get, the stronger the effect. So here's another one. This time, wow, spinning really quickly in there. You're going to feel that very strong. In fact, even if you started on this side of that, you might come up here, right here, and feel this really strong whoa. You might get pulled over this way. And so you kind of go, whew, right? And you get pulled all the way around to the other side like that and back up again. But now, see, we're starting to get further away again. So this time you might feel a little pull over, but then you kind of go, okay, not so bad. And because you're not as close, you might feel it a little weaker. And then, of course, the influence would get a little bit weaker. And then by the time you're over here, it's just a little bubble, hardly noticeable at all. But look what's happened to the magnetic field lines. If you look at the region over here on this side of the conductor, the magnetic field lines have been condensed together. In fact, if you count them, 1, 2, 3, 4, there's 5 of them, right? It's almost like they've been squished together. And on the other side now, there's only 3 of them. If we didn't have this green magnetic field caused by the current in the wire, it'd be even Steven on both sides. But it's not. And because it's not, what then happens is we get this pushing or pressure. You could kind of think of it like these purple lines are like rubber bands, and they're all stretched over here on this side. And so if they were to stretch out, they would push this way, and they would produce a very large force. I'm going to make a big arrow here. They would produce a force. And this force would push outwards in this direction. And this is what we call this is the magnetic force. When I was a kid, we used to call it the motor force, but I think a lot of textbooks are now just calling it magnetic force because the word motor force can be confusing with other forces that are similarly named. But anyway, it's a force caused by the motor principle, but it is a magnetic force because it's caused by magnetic field lines as they want to sort of even out this discrepancy that's been formed by the green field line. Now, if we look at this picture, we can see that there are a couple of things that matter. How strong is this force going to be? Well, let me go down a little bit. This force, this magnetic force, is going to depend upon, it's going to sort of depend or be proportional to, number one, how strong the original red magnetic field was. Now that's the magnetic field between the two magnets, this one, right? Not the green one. So this was the permanent magnetic field. So first of all, if you can get a stronger field between those magnets, you're going to get a bigger force, okay? The other thing it depends upon is, of course, the green magnetic field and how strong it is and how it's spinning. However, the green magnetic field is harder to describe because it's not constant. But we can describe it instead by what affects it, right? And so the effects are actually the amount of current in the wire. So if I put the amount of current in here, then that will make, obviously the green field will be stronger when the current gets stronger. And the other thing is the length of the conductor gives me some idea as to how much that green magnetic field effect would be. So those two numbers are sort of subbing in for the green magnetic field, and they're giving us the product of all of these things acting together, the sum of the two magnetic fields, so to speak. Now there is a little glitch. We've drawn a conductor that's going through at 90 degrees, perpendicular to the magnetic field lines. But it is possible to put a conductor on an angle, right? You might ask, well, how could you do that? Well, let's draw another picture just briefly. Let's say we had our magnets, but now we're going to look at it sort of from a side view. And here's the field, right? The magnetic field, because it was north on the bottom and south here. Well, the side view would be the wire running through like this. That's the side view of what I drew up on the other picture, right? If you kind of took this picture way back at the start and turned around on the side, right? I guess we have to look at this one. This one here, the purple one. The red lines are going up, the arrows going, the current's going in, but you can kind of turn it sideways and look like that. What I could do is instead, I could take a conductor and I could run it through the field this way, couldn't I? Which means that it is now at an angle right here with the field lines. And we call that, of course, the angle theta. And so if you want to bend your conductor at an angle to the field lines, then you would have to find out only not, you have to put in a little sine theta here, okay? Now, what I'm going to do is rewrite this in a different order. This is the way the textbooks like to write it. But technically, this is what it is. It's I times L, and then multiplied in a special way times B sine theta. And that special way is called the cross product. And it's a special way of multiplying vectors. And you'll learn more about this when you get into the details of vectors. Whoops, what am I writing? Productive. Just product, sorry. You'll learn more about this later, but I can give you a heads up. What the cross product does is, see, if you look at this picture, the current is flowing, say, this way. Well, what matters is how much of the current is flowing perpendicular, and how much of the field is perpendicular to the current itself. So here's a field line. I'm going to draw it bigger, and here's my current. Well, there's an angle right here, which we said was angle theta, right? But if I resolve my field line, whoops, that's backwards arrow. If I resolve my field into its components, the red field line has a component this way and a component that way. This component will equal B, which is the field's line strength, times the sine of theta. And that is the perpendicular component to the current. So what the cross product does is it says, let's multiply I and L. And then let's multiply that by the perpendicular component of B. Because that's all we want. Because that's the part that is actually involved in the molar force. And so it's really B sine theta, but because it's multiplying all the way along, you'll often see it written like this. I don't like that actually, but that's how your textbook writes it. And so I did it that way on purpose. But I want you to see that the sine theta really belongs to the B. That's what he's there for. And so in the future, when you take physics, your teachers and professors will probably think that you understand the cross product, and they will probably write it something more like this. Now, we're not quite done because we have this stupid proportional thing here. Well, what does that mean? Well, in order to make a proportion into something real, you have to make it into an equals, I guess. You have to add a little constant. So let's put k there for constant. IL, and then b sine theta here. Okay? Actually, I made a notational error. If you write it like this, you're supposed to just write it cross b. And the cross is supposed to indicate the sine theta part. So technically, yeah, that's a notational error. But it doesn't really matter. That was an extra little bit of information anyway. You can use this and still be just fine. Okay, so b sine theta is what cross b translates into. Anyway, interestingly enough, if we want to define the field strength as a Tesla, if we want to use Teslas for our field strength, then and we understand that 1 ampere of current on a 1 meter wire will give us a force of 1 Newton, right? Then we can assign k to equal 1. And so if k equals 1, this just works out to IL b sine theta. I don't know. I guess the book likes this to write it this way because it spells Bill, and maybe that's easier for you to memorize it or to remember it. But really, let's do it this way so it's nice and simple. Okay, now, that means that the B is measured in Teslas, which is what we're doing anyway. We're measuring our magnetic fields in Teslas. There are other ways to measure magnetic fields, in which case you'd have to use a constant to make this come true, to make it work out. But if we use B's in Teslas, then we get this. So here it is. I'll put a box around it. There is the formula that tells us the magnitude of the magnetic motor force that pushes on a conductor if that conductor is inside a permanent magnetic field and has a current flowing through it at the same time. It will literally get pushed. So in our picture, this wire will literally be pushed this way. You drop a wire in there, you turn on the current, and if you don't hold on to that wire, it'll fly out. It'll shoot out along that arrow. Now, of course, if you use some clever engineering, you can find a way to take that force and turn it into a spinning motion by using coils of wire instead of straight wires. But that's just clever engineering, and that's how we produce actual motors which do work for us. Or we can also run them backwards, and we can make them turn by hand or by using water or wind power, and we can actually spin them and create electric current, right? Think of it this way. If a force is produced when you put current through a conductor in a magnetic field, then if I supply the force and the magnetic field, and then what should happen is I should be able to supply, or I should be able to get the current part, right? This part, if I supply everything else. So if you push on a motor and you actually force it, you can get electricity to flow, and this of course is called a generator. But that's all the stuff that you would have seen in grade 11. The only addition now is this, which allows us to calculate the magnitude or the amount of that actual force. And of course it is a force, and so it's also measured in newtons. Don't forget that you have to remember your units. And so that's how the motor principle works.